One of our projects in the environmental direction has to do with the big question of how do we mitigate climate change. And right now, the conversation is very heavily focused on electrification, but it is starting to come to light that it cannot be the only solution. Electrification, fleet turnover does take time, takes on the order of decades, and it may not be accessible to globally. So one of the things that we're looking at is, what are some low-cost, near-term opportunities that are sort of a really good bang for your buck. And so we're looking specifically at intersections. It turns out that, especially in the US, we have so many intersections, and something that's very particular to intersections is you have to stop. You have to stop at intersections. You have to stop, then you have to reaccelerate in order to get through the intersection. Every time you reaccelerate, you're burning fossil fuels. You're contributing to greenhouse gas emissions. And we have done some sort of preliminary analysis that indicates that potentially up to 20% of land transportation CO2 is just wasted at intersections. It's in part due to our very heavy trucking industry, but just that 40% of vehicle miles traveled are sort of nearby to intersections. And so what I mean by wasted is that this is the energy that's spent just reaccelerating and idling at intersections, not the energy spent like doing productive work, carrying cars through the intersection. So we're looking at what can we do there? There's a very, very classic, well-known strategy called eco-driving at signalized intersections. And this is the idea of you can basically time cars such that when they get to the light, it's green. Okay, this is about timing cars, not about timing traffic signals. You can think of traffic signals as binary, like go or stop. And with that, you may have to stop and then you have to reaccelerate. With timing of cars, you can potentially have a smoother trajectory, and this has the potential to save on the reacceleration piece. Okay, so there's extensive studies, thousands of papers on this topic, very supportive as a low-cost, near-term intervention, but and this has been studied for decades, but we don't see almost any of it like in practice. And given sort of how urgent this climate crisis is, that sort of poses an interesting question as to why. And so we are investigating, we're sort of breaking down this problem into its constituent parts, and what we're finding in the literature is that the individual studies will look at individual scenarios for eco-driving. So individual intersections at this time of day, this route, but it's not really clear if it was effective at this intersection, would it be effective for another intersection? Would it be effective for Boston? Would it be effective for New York? How effective is it at a higher scale, at a higher level for something like climate mitigation? And so the largest project in my group right now is basically trying to model the impact. And it's still ongoing, so I can't say too much about the outcomes. But we're modeling 10 major metropolitan areas across the US, which comprises 30,000 intersections, each with different sort of roadway topologies, like grade of road, so elevation, different weather conditions, different travel demand and fuel mix, and so on. So this is one example where the curse of variety sort of kills you and has sort of, I would claim, has delayed the adoption, if this is indeed if indeed we are successful in confirming this to be effective, it would have delayed the impact of this very simple, low-cost, near-term intervention, because we could not actually estimate the outcome. And so each of these scenarios for each intersection with different configurations, different weather conditions and whatnot, is its own a sort of multi-agent control problem that needs to be solved. And so we're devising general purpose machine learning techniques that can solve not just one, but a whole family that's comprising of sort of tens of thousands of these scenarios.